Okay, for the next couple weeks in CH187, you're going to be working on the green crystal lab. And basically, you either prepared green crystals or some will be given to you. And we're going to try to figure out what the composition is and how much of each of the components are in this. So we're going to try to determine the empirical formula, okay? If you made your own green crystals, you'll have to isolate them at the beginning of class. And so to do this, they should be growing in a beaker in your drawer, and you will set up a vacuum filtration like this will be shown to you in class. But you'll have this Buchner funnel, and you'll have a, so this is the Buchner funnel with a piece of filter paper, and then we'll have a filter flask, which looks like an Erlenmeyer flask but has a sidearm on it that we can attach to the vacuum in our hoods. And what you'll do is you'll pour the liquid with the crystals in it onto the top here, and you'll collect the crystals on the top, and the liquid will go through and pass through into the bottom here, and you'll be able to isolate your crystals. So we'll do that if you need to. We'll do that at the very beginning of lab, and we'll give those a chance to dry while we take our quiz. If you did not prepare green crystals, then some will be given to you, okay? So basically, these green crystals were prepared by combining potassium oxalate and monohydrate, so it's got one water there, and iron 3 chloride, okay? And what precipitates out is this is kind of like a white powder, and this is like a brownish solution. And what we get are these green crystals. And so what that means is that there were several ions in solution that must have combined in some fashion to give us this solid. So when we combine these two reactants, we have potassium, we have oxalate, we have iron, we have chloride, and we have water all in solution. And it turns out all of them end up in the green crystals except for the chloride. It doesn't end up in there. We actually wash that away during the filtration process. So what we know is we know these green crystals have a formula where they have potassium, iron, oxalate, and water. And our goal is to determine the stoichiometry, or the empirical formula, meaning we want to know the ratio of each of these things. So we're going to sort of set the subscript with the iron at 1, and we're going to figure out, relative to having iron, how much of each of the other things do we have, okay? And so over the course of the 2 weeks, we're going to figure out this little by little using different techniques, okay? So this week, we're going to determine the amount of water and the amount of oxalate. So that's this week in lab, determination of the percent water. And so basically we're going to determine, if you have a mass of our green crystals, what percent of that mass is water and what percent of that is oxalate. And then the next week we'll do one experiment that'll allow us to figure out both of these. And so you'll be here 2 weeks in a row doing this experiment. Okay, so for the percent water, what we're going to do is, let me go back real fast. So our green crystals have some ionic compound, and then we see this dot, and we see water over here, and these are waters of crystallization, and oftentimes they can be removed if we heat the compound up. And if we heat the compound up, we can actually have the water evaporate, and we don't want to heat it too much so that we don't decompose the rest of the stuff. But if we can drive the water off, what we can do is we can go from having this hydrate that has water with it to just getting the potassium iron oxalate part of this without the extra water. And so in this case, when you have a compound that doesn't have any water, we say it's anhydrous. It's without water. Okay, and so what we're going to do is we're going to heat our green crystals up, and we're going to remove the water, and then we're going to figure out how much water we remove by comparing the mass before and after. Okay, so you're going to get a couple crucibles. Each person is going to get 2 crucibles. And a crucible is just a little porcelain dish that has a lid, and we can heat it up. And we're not going to heat it up super hot, but you can heat the crucibles up really hot, and that's what they're really good for. And so you're going to get 2 of them. You're going to put them in a beaker, and you're going to make sure that the lid is off, okay? So the lid is not going to be on, and we're going to heat it in the oven for 30 minutes, okay? And so we're going to try to dry that crucible. And then you're going to take it out of the oven. So we're going to have an oven in the back of our lab that we'll put everything in. You'll make sure that you have yours labeled or your beaker labeled. So you'll have a beaker with your crucibles and your lids, and you'll have a little label on it with your name. My name starts with an S, so I'll put it there. And then you're going to put that in your oven. And so we're going to let that heat for 30 minutes. We're going to do that right at the beginning of lab. And then once 30 minutes are over, we're going to take them out of the oven. We're going to set them down on the bench, and we're going to let them cool to room temperature. And then we're going to record the mass of the clean, dry crucibles. Okay, you never want to take the mass of something that's still hot. It's not going to be an accurate reading. Okay, so then what you're going to do is you have the mass of the crucible by itself after it's dry, and then you're going to add some green crystals, and you're going to get the mass of the dry crucible and the green crystals with the hydrate combined. All right, and then we're going to heat in the oven for 2 more hours, and you're going to make sure again that the lid is off. So whenever you take these things out of the oven, you can put when they're out of the oven, you can put the lid on to keep water from coming into your sample. But whenever they're in the oven, you want to have the lid off so that water can get out. Okay, so we put this in the oven, and while it's in the oven, water is going to leave. And what we're going to be left with is our anhydrous salt. It's not really that much of a color change. It's a little bit of a color change. It goes from being like a bright green color for the hydrate to being kind of a mint green color for the anhydrous compound. And so again, you're going to, after 2 hours, you'll take this out of the oven. You'll let it warm or cool down on the bench top, and then you'll get the mass of the dry crucible and the anhydrous salt. Okay, and depending on what's going on, we may have time to heat it again, but we may not. So we may heat it again just to make sure it really is dry, or we may just do the one-time heating. But what you can see here is that you're going to have, I don't know, do I have another room here? So you're going to have the mass of your dry crucible, and then you're going to have the mass of the dry crucible and the green crystals that are the hydrate. And if you subtract those two, you can get, if you take the mass of them together minus the mass of the crucible, you can get the mass of the crystals by themselves, right? So that's the difference between this one and this one. The difference between those two masses is going to be the green crystals. And then you're going to heat this up for 2 hours, and then when it comes out, you're going to have the mass of the crucible and the anhydrous crystals, and you're going to get the mass of those. And you may or may not have time to do for this. If you don't, you'll just cross it out on your sheet, and then you'll be able to have the mass of your crystals after heating, because you're going to know this mass here, and you'll subtract the crucible from there, and that's going to be the mass of just the anhydrous crystals. Okay, so you'll have the mass of the anhydrous crystals, and you have the mass of the hydrate, and so the difference between that will tell you the mass of the water. Okay, so you're going to be able to tell the difference of the crystal mass before and after heating, because the amount that it decreases is going to be the mass of the water. Okay, so once you know the mass of the water, you're going to be able to calculate the percent water in your sample. So you'll have the mass of the water that was driven off while heating divided by the mass of the crystals before heating, the green crystals that you put into the crucible. And so that times 100 is going to give you your percent water. And so you'll have two numbers, and you'll take the average of them, because you're going to have two different crucibles. Okay, so this you can write this on a sheet, but this information should also be in your lab notebook. Okay, so that's the first thing we're going to do, and that's going to be kind of passive, because a lot of the time things are just going to be in the oven and drying, right? And so the other thing we're going to figure out is we're going to figure out how much oxalate we have. And oxalate is a polyatomic ion, C2O4 2-. It's this guy right here. And what we're going to do is we're going to do a titration. It turns out that oxalate can react with permanganate, which is you may have used it before. It's a very dark purple solution. And so if we do that and we add a little bit of acid to try to get this reaction to go, what's going to happen is that these guys are going to react in a 5:2 ratio, and they're going to produce some carbon dioxide, and the permanganate is going to turn into manganese 2+, and then we're going to get some water. Okay, so what we have is we go from this purple color, and as soon as we react this, we're going to get a colorless solution. Okay, so we're going to look and see what that's going to let us do, but we have a color change. Okay, so that's going to allow us to figure out what's going on. Okay, so the moles of oxalate in your green crystals that you use in this experiment are going to be equal to the moles of permanganate that we use in a titration, which we'll look at in a second, times the mole ratio, the 2:5 ratio of permanganate to. Okay, so we're going to do this redox titration, and in here in your Erlenmeyer flask, you're going to have your green crystals, and you're going to add some acids. You're going to add sulfuric acid and phosphoric acid. And your handout tells you how much of each of those things to add, how much of the green crystals, how much of the different acids, and some water. And what you're going to do is you're going to heat that up. So you're going to sort of heat it up to sort of break everything apart. Okay, and so when we heat it up, we're going to sort of liberate our oxalate so it's ready to be reacted with. Okay, so we have the oxalate ready to do our reaction. And then in our burette, we're going to have the potassium permanganate solution. So you'll want to clean your burette out, and then you're going to fill it with your potassium permanganate solution, and you're going to make sure that it's going to be like a dark purple. You're going to make sure that the tip is filled here, and you're going to get that initial reading of what that volume is. Okay, and then what you're going to do is you're going to add the purple into down here through the burette. So we'll drip it in, and when it reacts, we're going to have that purple reacting with the oxalate and producing a colorless solution. Okay, so this down here is pretty close to colorless after you heat this up. It might be like a little bit yellowy or something like that, but basically what you're going to do is you're going to add the potassium permanganate, and it's going to react with our oxalate and use that up and produce our products over here. And then at some point all the oxalate is going to be gone, and then if you add one more drop of your potassium permanganate, which I'm not showing very accurately here, it's a dark purple color, at some point when you add that little bit of excess, so there's all the oxalate is all gone, now your solution is going to turn colors because there's nothing left. There's nothing left to react with. And so this excess is not going to form colorless manganese 2+, it's just going to be hanging out. And so what's going to happen is you're going to get, when you added just a little bit of excess potassium permanganate, you're going to see a light pink color. And it looks actually kind of like the phenolphthalein color that you're used to seeing with an acid-base titration. It's not the same, but that color, if you can look for the same color, okay? And so when you get that, you're then going to read your new burette reading, right? So you'll know where you started and you'll know where you ended, and so that difference is how much potassium permanganate you added, and you're also going to know its concentration. So you're going to have the liters of the solution times its molarity, which is moles times liters, and so when you multiply those together, you're going to multiply the volume times the molarity, and you're going to get moles of permanganate that you had to add. And so that's going to be useful when you know how much you added, that it's going to tell you how much oxalate you had in there. Okay, so that's what you need to do for this part, and that's what we'll be doing this week. Okay.